because if you went to 100 angstroms, there is almost no transfer, very little transfer. Now this is a kind of notation that I will use. This is my donor, that is my acceptor, and the distance between this capital R, you can say, okay, I will have the typical size of the donor with this RD and the typical size of the acceptor with this RA. And this R to the power of minus 6 is valid provided this capital R is much larger than either RD or RA. That's essentially the kind of limit that we have to think of. These are much larger than we have to to the power of minus 6. I will explain to you the reason why it is to the power of minus 6 in the next slide. Well, I suppose many of you would not have attended my previous lecture, and therefore this is, if you have attended, you have already seen this slide. So if you have said, my apologies. So see, essentially what is it that you have a donor, you have an acceptor, two molecules. And they have their own orbitals. This is what I can refer to as the highest occupied molecular orbital, for example, and maybe the lowest unoccupied molecular orbital, this term is and I have two electrons sitting here, but I don't only one of them, this is one electron, and I am not showing the other electron. Similarly, on the acceptor also, there is this HOMO and LUMO. Notice the notation also, psi donor, ground state, psi donor, excited state, wave function, and similarly, psi acceptor, ground state, psi acceptor, excited state. So what you do, you are going to excite this donor. So the donor has got excited, and it is going to transfer the energy to the other acceptor. How does it do that? When the answer is that there is Coulombic interaction. There is Coulombic interaction between this electron and that electron. Correct? So what does Coulombic interaction do? It basically causes this electron to get excited, and if this gets excited, naturally the other electron will come down. Okay, so this is the process essentially, and if you think about it, you will say that there are 4 orbitals involved in the process. Right? 2 on the donor, 2 on the acceptor. So I suppose you would have studied a little bit of quantum chemistry. So I myself have been trained as a quantum chemist. So if you ask, I want to calculate the rate of this process, how would I do that? The answer is that I will ask what is the matrix element responsible for the process. As a quantum chemist, this is what you will do. So therefore, how do I calculate the matrix element? In fact, why is it that it is R to the power of minus 6? For that, I write down what is referred to as a matrix element. Now remember, this is a 4 orbital process. There are 2 orbitals on the donor, 2 orbitals on the acceptor. So it has to be determined by these 4 orbitals. So therefore, I would have an expression which looks something like this. I have a 2 orbitals on the donor, which I will written with red color. 2 orbitals on the right? And then of course you have Coulombic interaction. As you all know, Coulombic interaction is between the 2 electrons. So naturally you will have the distance between the 2 electrons sitting in the calculated in the matrix element. In fact, 1 by the distance because it is Coulombic interaction. So then you have to integrate over all possible positions of the first electron as well as those of the second electron. So that is what you have to do in principle. Simple to do, even though in practice it is a little bit complex to do it.
So, this E and G are they symmetry? Sorry? E and G, AG and AE. Are they symmetries? Or
in the symmetry, you molecules.
No, and he's asking about AG and AE. Those methods. G and E.
Ground excited.
This is ground. Oh, they are not symmetry. They are ground. Not red or anything like this is ground state. G stands for ground state, E stands for excited. I told you I had my notation earlier. This is the HOMO on the donor, right? Like I just put G. Everything is in the ground state. And this is the excited state on the donor. Similarly, this is on the acceptor, and that is the similar thing on the acceptor. Nothing to do with the similarly species and so on. this is what it is, and therefore you see that if you look at this, you see it is nice. Why is it nice? Because it is a coulombic interaction. Coulombic interaction between this product and that product. And this product, if you look at it, it is actually some kind of density, right? I mean, the wave function multiplied by wave function, that is something like wave function squared. So this is some kind of density and on the donor, and that kind of density on the acceptor. These are interacting completely. That is what they are doing. So therefore, I have to write the. I have to calculate this, but this calculation can be made simply. It is essentially two charge densities interacting, one on the donor and the other on the acceptor. So if the two charge densities are not very close by, then what I can say is that the simplest thing is to have the dipole of the first density and I calculate the dipole of the first density, I calculate the dipole of the second density, and then I know it is just dipole-dipole interaction, right? So therefore, essentially I shall approximate. So actually doing this in the grid, I shall just calculate the dipole of this density, dipole of that density, and I know exactly how two dipoles are going to interact. You would have also studied electron dynamics, you would know how to calculate the interaction between two dipoles. This density actually in spectroscopy, you have a notation, you have a word for it, it is referred as transient density of the donor, and this is usually referred to as the transient density of the acceptor. So these two charge densities are interacting, as I have told you, it is electrostatic interaction, and therefore effectively I can approximate these two charge densities by their dipoles. They are actually referred to as transient dipoles. If you have studied spectroscopy, this term would have been told you already. So this is transient dipole on the donor, that is transient dipole on the acceptor, and these two are interacting electrostatically. And if that happens, what happens? You know the expression. You know that when dipole-dipole interaction goes like 1 by distance to the power of 3. That is the matrix element, and the actual process is if you wanted to calculate the rate, the actual process would have matrix element square. This always happens in quantum mechanics, as you would know. And so therefore, if the matrix element is going like 1 by r to the power of 3, the rate will go like matrix element square, and therefore it is 1 by r to the power of 6. So this is essentially the reason why the rate of energy transfer goes like 1 by distance to the power of 6. But the question then is, can I have some other kind of dependence? Can I have not r to the power of minus 6, but something which is probably r to the power of minus 4 or minus 5? Why would I want to have that? Because suppose it is r to the power of minus 4, then as you increase the distance, the rate of energy transfer will not follow so quickly, and therefore I might be able to have a ruler, right? Something to measure distances, not up to 100 angstroms, but maybe up to 200 or 300 angstroms, and therefore it can be very useful if I can have that. That is the reason why people have been interested in this. So the question is it possible? And the answer is it has been. When we started getting interested in this, when we started working on this, essentially it was because there was a paper which reported not r to the power of minus 6, but something that is different. So let me tell you what it is. It is actually resonance energy transfer from a dye molecule to a metallic nanoparticle. So what is the process? This is your dye. You are going to excite it, and then you see there is coulombic interaction, which is shown by this wavy line. As a result of which energy is transferred to the nanoparticle. A nanoparticle, this is a metallic nanoparticle, and metallic nanoparticles have electronic excitations, okay, because it's electronic energy, it's a lot of energy, and that lot of energy is transferred from here to there. And nanoparticles have excitations which are classified usually as plasmons. Plasmons are collective oscillations of the electron, and this excitation which large number of electrons are moving, not just one. And you can have an excitation in which maybe one electron goes from an occupied orbital to an unoccupied orbital, where it was electron fold pair excitations. So So you can have both the kinds of excitations. And the question is, imagine these are the possibilities. Then what is the rate of energy transfer? How does the rate depend upon the distance? Now let me tell you of the experiment. See what the experiment, what they did was they had a gold nanoparticle. Size was 14 angstroms. 1.4 nanometers, that was the size of this particle. And here they had a dye. Remember the name of the dye. But you see, you have to keep the dye at a particular distance from the nanoparticle. So how do you do that? You attach the two to the end of a finite strand of DNA. Double-stranded DNA. Why double-stranded DNA? Why not single-stranded DNA? It's very simple because you see, a double-stranded DNA is almost like a rod, and therefore the separation will not change. But up to maybe something like 200, 300 angstroms, double-stranded DNA is almost like a rod, right? Because of the two strands. If it is single-stranded, it will be very flexible. So what they did was they varied the length of this spacer and studied the rate of energy transfer. Okay. From here to there, how do you study the rate of energy transfer? The answer is this. Normally, if you excite the dye will fluoresce. So you can see the fluorescing, right? But then if there is this nanoparticle, what will happen is that when you excite the dye, it will fluoresce, but in addition to that, it will also transfer the energy to the nanoparticle. And if it is transferred to the nanoparticle, naturally fluorescence will be less. And so by studying how much the fluorescence increases, you can estimate the rate of energy transfer.
So you have to worry about any energy dissipation within the various portions in the DNA itself.
No, because it says the electronic energy is very large. Right? DNA, what can you do? It can either get electronically excited, or that energy is not there, or it can get electrically excited. In fact, we did worry about energy transfer through DNA. So, the experiment says that it is not their rate, but instead they claim that the rate goes like 1 by distance to the power of 4. And that is very nice and very interesting. It is true, it is very nice and very interesting. And not only that, they observed energy transfer up to 250 angstroms, not the 100 angstroms.
So the band gap of this
Well, we will come to that. Depends upon the size. So, they call this particular process nanoparticle surface energy transfer (NSET). And they said it is different from usual process FRET, because in FRET, which is what I discussed earlier, FRET the rate will go like 1 by distance to the power of 6. Whereas in this case, it is e to the power minus 4. This d is actually distance of the dye from the surface of the nanoparticle. That is okay. Not the center to center distance. Capital R will be the center to center distance, while d is the distance just from the surface of this nanoparticle to the dye.
and these are single molecule.
But it is not a single. You can do it single molecule, but it is the way the experiment it is an answer. But I am not going to discuss the details of these things, but what I want to say is this kind of energy dependence. You see, they proposed this d to the power of minus 4 essentially because there were theory papers, there were external papers published long ago in the surface science literature. And this kind of dependence was known in a different program. I'll tell you what the program is, so I will not go into the details of this. What you imagine is that you have a metal surface, and you put a diatomic molecule, maybe carbon monoxide or some diatomic molecule at some distance away from this. And now suppose you excite this. Vibrationally you excite, not electronically. Vibrationally excite this vibration energy can be transferred to the metal. And in the metal, what happens? The metal there is an electronic excitation. The metal has a continuum of excitation. So therefore, from an unoccupied partner first before the experiments were done, and he predicted how that is the process. You vibrantly excite, and he said that okay, the distance dependence is actually this is to the power of minus 4. Okay. And he essentially said that these are simple electronic excitations where you take an electron from an occupied orbital to an unoccupied orbital. Now you see, now I want to compare this with the nanoparticle. See, if you had a metal, as I told you, these represent the occupied orbitals, those represent the unoccupied orbitals, the commemorate, I suppose you would know this. And therefore, you see, I can have any kind of excited, any energy excited. If you give the metal a small amount of energy, you can always find an excitation which will have the exact same energy. So therefore, you can have an excitation of very small energy, or if you want a larger energy, that is also possible. Why? Because the allowed energy levels form a continuum. You have a continuous spectrum of allowed energy levels for a metal. For a bulk metal, for a semi-equivalent metal, that is the way it is. But in comparison,